All right. Well, good afternoon, everybody. My name is Brandon, and I'd like to start today by telling you a story. Now, I moved into my current house about 3 years ago. It's an older house in Austin, Texas, but it was heavily renovated by the last owner, whose name was Zeke, by the way. Great name. Some of those renovations were good, some of them were bad, and some were, well, I can't quite think of any other way to describe them than to tell you that my wife and I actually created a verb form of the last owner's name to describe some of the ill-advised things that he chose to do to our house. What is now our house? Yes. So to have Zeked something is to have royally messed it up. Installed a basement or safe room under the patio, which no one does in Texas without properly sealing it to keep out the water. Yeah, you Zeked that, buddy. Pretty big. Hired your next door neighbor to do electrical work and then refused to pay him. That's a big Zeke. You're going to pay for that one for sure. And by the way, this actually works in one's personal life. It doesn't just apply to these personal projects. So for example, stayed up too late the night before a talk, working on the demos. Yeah, you Zeked it big time. One of the many Zeked up parts of this house is the appliances in our kitchen. They're all top of the line, I suppose you could say, but they've been very odd from the start. This includes our dishwasher, which is this nice brushed metal LG that you would expect to see in most newer homes. And it served us well once we cleaned the filters and purged a Zeked up smell emanating from it when we moved in. But until recently, that is, it started actually doing a few odd things that were hard for us to really identify. First, it got louder. It was never really a quiet machine, even though it was a newer machine. They're all supposed to be so you can't even hear when they're running half the time. Like half of your stress about owning a dishwasher now is it actually running? I don't know if it's running. I can't hear anything. You know this one's running. It's not a problem. At least that's definitely what we noticed very early on. And then it got louder sort of out of variance from what we expected. And this was noticeable even to me, and my hearing is not great compared to my wife's. And if I agree with her on noises, then definitely it was loud. And then if we ran it under certain conditions, it would actually trip the GFCI breaker in another part of the kitchen, and what would seem to be an unrelated part of the kitchen. I don't know how that happens. And this would happen when there were other appliances running in the house, like when the washing machine or dryer were running. Again, machines in a totally different part of the house. And these were variances that were observable to my wife and I as human beings. We saw these things. We saw something that happened out of our normal expectations, so we were able to fix the issue. But what if this had all happened during a time when we were away from our home for a couple of weeks and the same pattern of behavior occurred and there was no one around to witness it? Or better yet, what if this was an industrial washing machine on a floor with over 1,000 other machines and only a few humans to monitor all of them, and something went wrong then? And I think this class of problems is why we tend to really be fascinated with this idea of machine learning. We know our limits as human beings. We know what we can detect, but we also know that we can't always be present. We're not always available to detect a problem before it happens. And in many cases, we can't detect a problem. But we're fascinated by this idea of using computers to do things that we may not be able to be present for, or things that we can't. And this example, I think, also illustrates what I consider to be two really key factors that I want to talk about today, or I want to highlight under the context of machine learning. And that is that the data that's so critical to machine learning is not this mythical cloud-based construct. All the data for machine learning doesn't come from Kaggle. It actually comes from the real world. It comes from the environment where real things are happening. And second, that machine learning is fundamentally a human practice. We talk about machines, we talk about the cloud, we talk about huge computers, but this is still fundamentally a human science, or even human art form in some cases. So my goal in the talk today is to convince you of three things. The first is that machine learning is really just human teaching. The second is that the exercise of training and refining and creating data sets or creating models is actually meant for the cloud, but that the real work of machine learning and the future of machine learning is happening in the Internet of Things. And if I don't Zeke things up, we'll maybe even get to do a few fun demos along the way. So let's go ahead and get started. Now, I go to machine learning talks at conferences. I've been to a bunch of them today. So because this is a machine learning talk, I have to show you a Venn diagram, because that seems to be what we always like to do, is show you the Venn diagram of what these various things mean. I'm going to spend the majority of my talk on the third topic. It's going to be on the IoT side of this conversation. But I want to level set a bit and tell you that I'm not going to talk about artificial intelligence. It's not why I'm here. I will say that it's a big generic term that means everything, and let's just agree on that and move on. What I do want to spend time talking about is machine learning that as the subset of artificial intelligence, but the type of subset that's really focused on training computers to accomplish things that would be hard for us to program algorithms for, either because we don't know the algorithm or because it's really hard for us to express it easily. And this varies from traditional programming. In traditional programming, we provide a computer with an input and an algorithm, and we say, okay, now give me the answer, calculate the output. What would probably be an oversimplified, but I think still relatively accurate way to describe machine learning is to say that we actually provide a series of inputs and answers, and then we ask the computer to actually give us an algorithm, which we actually call the model. We actually tell it to predict for us the best way that you can think to create an algorithm that reduces the error that comes out the other end. It gives us the best outputs. And then deep learning is a subset in itself of machine learning that's designed to make sense of large amounts of complex data. This does so by using layered approaches. When anybody talks about deep learning, we love to show you these wonderful neural network diagrams, because they look really complex and cool, and that's awesome, but also because they actually can help illustrate the complexity of what happens as data moves from one part of a network to another. Fundamentally, what happens with neural networks like those that are illustrated here is that complex data sets are simplified from one step to the next. And they're simplified in the sense that features are extracted from one piece of the model to the next. From raw pixels, a machine can actually figure out to start to draw lines and boundaries. And then it can figure out facial features. And then it can finally make a prediction or classification based on that. My favorite explanation of machine learning in general, and specifically the subset of deep learning, comes from Andrew Trask and his book, Grokking Deep Learning from Manning. I highly recommend everyone get this book. It is well worth its weight in gold. It's a phenomenal, phenomenal book. Really easy to understand, even if you have no prior experience in the field. And in one of the early chapters in the book, what Trask uses as an example is to imagine that you're in a country where the stoplights are different from what you expect to see. So you walk up to a stoplight or an intersection, you see three different lights, the colors are irrelevant, which is why they're not included in this example, and some combination of those lights tell pedestrians whether to walk or stop, or tell cars whether to walk or stop. Now you don't know what they mean, so what do you do as a human being? You sit back and you observe. You watch what 2 means. People aren't moving. Now you see the middle one is on and the right one is on. The first one is off, so people are walking. You watch a third pattern. It doesn't take you long as a human being to actually figure out maybe 4, 5, 6 iterations of this, that, okay, it's the middle light. When the middle light is on, I can walk. The other two are effectively irrelevant in this case. Our brains are very good at observing these kinds of patterns and finding correlations. And it turns out at its core, this is really all that deep learning is. It's providing a set of inputs and outputs and then devising approaches, architectures, parameters, tuning to help the machine find the right correlation. First, we break our data set down into something that a computer can understand in the form of numbers. Then we actually create a program that illustrates the exercise of creating the model and running through iterations over and over again. And then we set the machine off to do its business. At that point, it then runs the model over and over again. It basically starts with random numbers as guesses, and then over time finds the best algorithm or the best set of weights and measures that give it the lowest error, that give us actually the best correlation. Machines are designed in this case to find the best correlation between the inputs and the outputs. But the whole reason that I'm sharing this example is because even though machine learning puts the computer at the center, even in the terminology, machine learning is really just nothing more than human teaching. We provide it with the inputs and the outputs. We tell the machines what to find, what to think, what to use as important, or what to use as the framework by which it creates the model. The human is the essential engine in machine learning because it takes a human to create the inputs and outputs, to do the data preparation, to actually select a model architecture, and then to train, evaluate, and tune the model. And this is an important principle and one that we're going to come back to because in the realm of ML, we've spilled a lot of ink about the importance of computers and the importance of the cloud. The human is an important factor, and then the world around us, the places where data is actually occurring, where we're actually finding the data that's feeding our models, will become very important as well. But before I get to that last piece, I do want to spend a moment talking about the cloud and putting it in appropriate context of where the work, the valuable work, where the role the cloud plays in creating value in the context of machine and deep learning. But I want to talk about sort of the phases of the machine learning process to put this in the right context, and that'll feed into the last part of the discussion. I hinted at this already, but it's important to be explicit because it will frame my sort of thesis about the importance of the IoT here at the end. And that is that machine learning isn't really done in one place. Machine learning isn't something that you do in the cloud or do somewhere else. It's not the domain of these giant cloud providers that are burying their data centers under the ocean because that's the only way they can solve their cooling problems. It's the domain of everyone that's involved in the process, because the process can be really broken down into three parts. There's the development, the creation part, the training part, and then the inference part. The creation part is one that many of us are already familiar with. It's the work of the data scientist. And this is all work that tends to be done on local development machines, right? These are the dev tools of the data scientist, of the machine learning engineer. There are others that are not on this list, but it's a very Python-heavy environment. There are other tools in .NET and the Java space and C++ for doing this similar kind of work. But again, all of these are development tools. These are developer tools that are being executed on a local machine. And once a model is created or selected, the next key step is model training, the process of actually running the input data through model architecture. And then it's many layers and thousands of times as the machine attempts to actually find to reduce its correlation and find the right model. Now, very few of us that do this kind of work do this work locally on our machines because we don't like waiting months and weeks for models to actually train. So a lot of times what happens, this is where you hear about the cloud. This is where we use things like Jupyter Notebooks deployed in cloud environments, or we use Google Colab, which is actually a really cool tool that's integrated into Google Docs, which is pretty amazing. Or to use Azure ML or Amazon Machine Learning to actually do the training and experimentation process. But let me actually show you briefly what this looks like with the model that I've actually been working on. And the model, this is going to feature in a couple of my demos today. And the model is actually a emotion classification model. So this is based on a data set from Kaggle. Says the guy that 5 minutes ago said not all data in machine learning comes from Kaggle. Mine did in this case. And this is an emotion classification data set that's got about 29,000 images, 48 by 48 grayscale images of people making various different faces that have been then labeled as angry, disgusted, fear, afraid, happy, sad, surprised, or neutral. And as you'll learn as we go through this, neutral is the machine's way of saying, I don't know, could be anything. Okay, so you'll see that happen, might even happen in some of the demos. But the others are classified or labeled in that way. And then we can actually use that to create an interesting convolutional neural network that can take an image, a color image in this case, and actually give us a prediction of what the emotion is on the other side. I'm using Python, TensorFlow, and Keras for this inside of Visual Studio Code, and quick plug for the greatest Visual Studio Code theme of all time, Synthwave 84. Please download it and use it. It's amazing. You have to hack your installation, but it's totally worth it. And my process of loading this, I'm not going to belabor this point. If you're familiar with this, great. If not, I encourage you again to check out books like Trask, Grokking Deep Learning. I want to share sort of what this looks like from start to finish. I have a data set. In this case, my data set is represented as a giant CSV file that's so large, I couldn't load it up into Google Colab. And then I'm taking the data, specifying an image size, to setting the image size, and then going through the process of loading and transforming. And actually, as I go through this really quickly, I want to actually start the prediction. No, not that one. And actually start the training to show you some of the outputs. I'm not going to train this entire model because this conference would be over before it's probably done if I ran it on my machine. But I go through the process of actually loading the data, getting a pixel representation, pre-processing the individual inputs, and then I create an image data generator. The image data generator actually is really useful in the context of creating convolutional neural networks, especially around image recognition, because they give me the ability to take a small data set, which 30,000 images is actually a pretty small data set, And then I make it larger by randomizing photos. So I take a bunch of the photos and I rotate some, I zoom some in, I zoom some out, and now one photo can become 5 different photos. And that gives the model more varied data to learn so that it doesn't overfit and learn its training data so well that it has a great training loss and a terrible validation or real-time performance loss. So I'll load the images in the image generator, and then I use Keras to actually build out the network. And the network is a several layer network that does convolutions on the images to find features, dropouts, again, to keep the model from overfitting. And then I go through this on 4 or 5 separate layers. I'm not going to walk through all of these before I actually then go through the process of setting up logging, and then the fit generator. This is the piece that when I call this, now it's time to wait for a long time while the model actually goes and gets created. The output models are then evaluated through these callbacks, and then as the model improves over time, I get a new version of the model that's actually saved in my models folder. And so what you end up getting, and I'll share the link for this at the end, the GitHub link for this at the end, is the model looks a lot like this giant, very, very deep network that ultimately at the end, and I'm not going to zoom in on this, but this classifies down to 7 different emotion types at the bottom. And then what I got over training is a training and validation accuracy of around 66%. That's actually I would never deploy this model in production, but it's kind of interesting to work in a fancy demo that will never actually get used outside of a conference presentation. 2/3 right? Great. I think we can absolutely go with that. So I kick this off in the background so you can actually see what happens when I go through the training process. I just very quickly take a look at some of my data to make sure I'm getting the right thing, ignore some warnings, and then actually print out the architecture of the model. So this is just a text representation of the visualization that I just showed you. And then it starts running through the first of its 110 epochs as it actually crunches all these numbers and tries to get the best correlation possible. And you'll notice that my accuracy right now is crap. It's like 24%. If I were to keep running this over the next several hours, days, weeks, months, or years, it might finally get itself up to 66%. I'm not going to keep on running that. The point was to share that sort of the process of doing that, everything that I just did was on my development machine. The training piece, when I kicked that off, I would have been far better off if I had deferred that at some point, loaded in the cloud, run an Azure ML experiment, something like that. But the actual development and evaluation piece, when I'm actually shaping the data, looking at it with pandas or loading it up in another visualization, all of that is happening actually on my development machine. And it's also important here to note that this is a very iterative loop. It took me several weeks of work to get to that point of tuning the different parameters to figure out how high I wanted my dropout to be, tweaking some of the things on the image data generator. Maybe I wanted to zoom by 20% instead of 10%. Like if you've done this kind of work before, those are the kinds of things that you make tiny little changes on and then run again, and then make another tiny little change and run again until you get something that you feel pretty happy with. That process is very, very iterative, and it starts from when you define the task all the way through collecting data to actually then training, testing and evaluate the model, executing, and then deploying until you actually finally get to the end. And when you get that model deployed, you get to the fun part, the whole reason that we do this in the first place, which is inference, right? During training, we're instructing the model to learn by tuning its weights to reduce error, to actually find us the best correlation in the network. Those weights are then applied to against data that the network has never seen before to actually make a prediction. And the tools that tend to be used for prediction are things like, in the case of images, OpenCV, TensorFlow, Keras, all of these. And other tools have predictions, have tools for actually running predictions in post-evaluation or even running in the cloud as well. So let's take a brief look at what that looks like. With the model that I just created, we can go ahead and run a prediction. So now I'm going to execute predict.py. If I didn't mess anything up, this will take 2 or 3 seconds. Now notice too, this is my execution time. I had an image already saved. My execution time on my CPU for inference was 2 seconds, which if I were running in the real world, that's crap. That's terrible. A lot of times when I need to actually run inference, it's against data that's streaming across a lot faster. For the case of a demo, this is fine. I ran an image. I'll show you the image here in just a moment. The image that I ran is one that I prepared a few weeks ago, that one. So I took this wonderful image of myself that looks way too large now on that screen, ran it through the model, and the modified version is I'm angry. I don't know if that's necessarily correct, but I can see how the model would think that that's an angry face. I guess it kind of is. I'm raising my eyebrow, what have you. That's the inferencing step. That's the point at which we can actually take all that hard work and get something out the other side. So, once we've built and trained our model, we're not going to run those on our development machines for a number of reasons, but we often want to deploy it somewhere. Now, most of the time, or at least today, this is a cloud-based endpoint, something that's hosted on Azure, AWS, or Google. A lot of times we deploy these models for inference in another location. That makes sense that we would do that. We create serverless functions and things like that. They're also great products if you're doing something like I'm doing, like computer vision or speech or language. There are APIs that are already out there. You don't have to go through the painful work of several weeks of trying to create something that's only 66% accurate like I did, when you can get some of that same functionality via cloud providers and models that are tuned and cared for and very, very professionally done, not done by some hack amateur that spends more of his time on microcontrollers than he does on these kinds of things. So let me actually show you a demo of that, because it's useful to see sort of the same idea, the same thing that I built here in training. I'm sorry. Let me take this over here. Hold on. All right. And so this was the local training step, the local prediction step, right? I loaded up this image again in an OpenCV, evaluated. That was sort of the modified photo I just showed you a second ago. But if I were to use a cloud provider, I could use the Azure Cognitive Services Face API, which they have as a Python package called Cognitive Face. I can load that up, provide the right config values, my API key and URL, provide an actual image to grab, and then I go through the face, I call the face.detect API. It gives me some landmarks, and you'll notice that the attributes that I can provide are quite robust. It's not just a motion detection I can get from that API. I can also get evaluations on age, gender, head pose, smiled, facial hair, glasses, emotion, all these wonderful things that can actually come for free as a part of using that API. So when I call this, and I'll call detectface.py, and you'll see it'll copy the output payload here. This is the image. The guess that it made was happiness. Yeah, that's probably pretty good. It's a different image that I provided as well. But you'll notice that everything else that I got there. So I'm very flattered. It thinks that I'm 35, so thanks. This is wonderful. It's not correct, but I'll take it. And there's a bunch of other information on here as well. I'm not wearing glasses. Here is the bounding box for the face rectangle. I have 40% of a mustache and 40% of a beard, apparently. Not a full mustache or beard. I don't know if I'm insulted by that or not. But again, you can get a lot of information from these APIs, and those are already built for you, and the work of maintaining them is not yours to manage. But so far, the delineation of where things happen in the machine learning process has been pretty straightforward, right? We develop models locally with local tools, and we train and refine those in the cloud, and then we run inferencing by accessing cloud-based endpoints. But one thing that we haven't really discussed yet, and that I keep hinting at, is that where the data is coming from that we're feeding into these systems, right? Where is our data for inferencing actually coming from? And where is our training and validation data actually coming from as well? And that's what I want to spend the rest of the talk today actually going through. And that is the real work of machine learning in the IoT, things that are happening at the edge, and then opportunities or things that I'm seeing that are really exciting about the future of machine learning at the edge and in the Internet of Things. So, first, let me dispense with some dumb terminology. I don't like the term edge computing. I don't like the phrase the edge either. And let me tell you exactly why. Now, when you hear about machine learning in the IoT today, it comes up in the context of doing machine learning inferencing at the edge. And what people mean when they say that is that you have computers that are kind of like Raspberry Pis, but more expensive with better processors. And these edge computers can actually do inferencing for you. And we'll talk about what some of that means, and that's really useful. And I have a demo of that today. But to assume that that's something different than the IoT is what I tend to have an issue with, right? Traditional IoT installations tended to look like this. You had a network of sensors and actuators collecting data, and these devices would send all their data to the cloud for analytics and processing and more. There's a huge gulf between these devices, right? You had a cloud with lots of power, and you had an Internet of Things with lots of devices, right? You had small microcontrollers or MCUs and single board computers that really couldn't do much more than manage connections to sensors and actuators and backhaul data into the cloud via Wi-Fi or cellular connections. But in recent years, it's become common to introduce a third type of location or a third type of device into the mix, what we refer to it as the edge. I don't know what this phrase means. I don't know what the edge actually indicates. I don't know if it's this magical DMZ between the cloud and the IoT, a place where Irish lead guitarists can spend some of their free time if they so prefer. I don't understand. What I do know is that what it's meant to convey is that is to be a location where computers that are more robust than what we have in our MCU-powered IoT networks can actually offload some of the work of the cloud while having more power than microcontroller units tend to have today. All that makes sense. This is fine. I don't have an issue with that. It's a bit of both style of computing device. But I want to be clear about something. There is no barrier between the edge and the IoT. This is a false delineation. The edge is part of the Internet of Things because it's fundamentally not part of the cloud, right? When we talk about edge computing, we're talking about adding additional power and capability to our IoT networks and our IoT devices, full stop. And whether it's in the edge or on IoT devices, the source of the data that machine learning models need, not only for inferencing, but for actual training, is coming increasingly from these locations, right? If you're talking about image recognition, or you're talking about real-time neural networks that rely on time series sensor data, that data comes from sensing networks. Sensing networks are fundamentally and increasingly internet connected. These are IoT networks. Now, given all that, let's talk very briefly about the reason why ML inferencing has become so popular in this context of the IoT. And there's really three major reasons why it's appealing to a lot of us to try to do inferencing closer to where data is actually being collected. First is just the scale and volumes of data that we're dealing with. Now, we've actually passed the point where the number of IoT devices that we have deployed around the world is larger than the number of non-IoT devices. There are more IoT devices than there are mobile and desktop devices, period. And the growth between now and 2025 is expected to be about 150% of IoT device growth versus 14% of non-IoT device growth. So the reality is that there are more of these small MCUs and single board computers, and there will continue to be more of them many, many times over than what we're deploying than what we're using for our mobile phones or for our desktop devices. And as more and more of these devices come online, we will collect more and more data from them. As we collect more and more data from these devices, we will increase the compute capacity and capability of our cloud platforms in order to compensate. But there's one weak link in this entire process that I hope my slide made relatively glaringly obvious to all of you. Because while the cloud can theoretically scale up to account for more and more data, and we know that we're going to have more and more devices, in many cases, the pipes that we're using to send the data to the cloud are not in themselves infinite. They themselves can be relatively fixed, and there's only so many things that we can do to manage timing and how we actually scale data to the cloud. And the nature of machine learning is a very data-hungry field. We will not probably see a trend in machine learning where people talk about, hey, you know what, y'all? I think we could do more with less data, machine learning. No one is going to say that. We continue looking for ways to get more and more to power our networks. But if we don't have to do inference in the cloud, we can actually buy ourselves a lot of benefit. This changes the dynamics of how we send data to the cloud and even the kind of data that we send in the first place. Because as I said before, with inference, we provide a volume of inputs and we use the model to predict the output, right? And oftentimes that's the prediction is the thing that we're actually looking for. We can send sensor data like speed and accelerometer data and capacity of a pump and lights and light level from a light bulb. And we can send all of these things back up to the cloud, but we're not sending these things for the sake of getting those raw data values, those raw sensor values in the cloud itself. Many times what we're looking for is the prediction that comes out the other end. That's the thing that's interesting to us because it's the thing that we use to take action. In the context of the IoT, it's often the thing that we use to solve problems before they happen. So doing inference closer to the edge means that we can actually respond to the data that we're getting to IoT devices from IoT devices faster. And this is very important in the holy grail of IoT use cases, predictive maintenance. So consider an industrial setting with a number of machines churning away 24/7. And because these are machines that are mechanical devices, we need to monitor their vibration, right? Machines that vibrate tend to break down over time. And so each machine is fitted and connected with an IoT device that has an accelerometer that's constantly monitoring vibration of key motorized components. And when I mean constantly, I mean it is sampling vibration 1,000 times a second. And this is not abnormal. So if we've trained a neural network that knows what an out of variance vibration pattern looks like and that's indicative of a machine about to break down, then that's not easy to begin with. The data collection process for that is a challenge in and of itself, don't get me wrong, but let's assume that we have one. And this network knows what variances look like and can then actually specify that the machine needs to be serviced ahead of time. Streaming all this data to the cloud in order to run this inferencing is not only very expensive, but as we discussed before, it's time consuming. And it also means that we can't perform predictions against our fleet if the network is offline or down for any reason. Loss of network connectivity is a big problem, and it'll only continue to become a bigger problem the more data that we actually send to the cloud. But if we move inferencing to a device that's on the edge of the network or in the IoT itself, you get the benefit of machine learning with the speed of local processing, and then you can identify when an out-of-variance machine has misbehaved. Finally, inferencing at the edge is really fundamentally more secure, which is another really important aspect of machine learning and something that we're talking about in this space quite a bit. Because when we're sending only outputs or predictions back to the cloud and not all of the input or source data, it's much easier to build ML and IoT applications that are resilient to manipulation and respect the privacy of the consumer or the company that the data is being collected from. So we go back to my machine vision as an example here and discuss face tracking again. So think of the earlier demo that I did with the Azure Face API. So in order for Cognitive Services to give me anything useful, I needed to provide it with an image as an input, which means that I have to transfer a file across the internet into the cloud to get the thing that I want, which is the prediction, which I then can use or store. Now, Azure doesn't store the image, but the very fact that I transfer it up does introduce privacy considerations and an attack vector in my solution. But if I use edge inference, on the other hand, the image or the video stream never actually leaves my local network. And what's interesting about this is with the prediction that I get out the other side, I showed you that JSON payload, the data that actually represents my face or the prediction that was made by the local inferencing step cannot be reassembled into the source image. There isn't anything identifying about this that says, hey, this is Brandon and he's not really 35, but don't tell anybody, right? There isn't anything built into that data set that allows my privacy to be violated. So the solution is fundamentally more secure. Now, because this is an IoT class problem, we solve it with IoT class devices, right? So there's a couple of great solutions out there. There are many others, but I'll share just a couple here because these are devices. The kind of work that we're doing, I showed you inferencing of the image of my face took 2 seconds on my MacBook Pro. It'll take a lot longer on a Raspberry Pi, right? So these are not the kinds of solutions that we can solve necessarily today with the class of Pi-like single board computers that we have. So there are newer computers out there that offer similar sorts of capabilities. Two that are interesting are the Google Coral and the NVIDIA Jetson Nano. And these are both devices that are purpose-built for doing machine learning inferencing at the edge. Now, the Google Coral, their approach is actually they created an ASIC. They created a custom piece of silicon that represents a module that has what they like to call an edge TPU module or TensorFlow processing unit. Their module runs inside of this device and really does nothing but all of the matrix multiplication that needs to happen in order for machine learning inferencing to take place. It also has an ARM quad core, a quad core Cortex ARM A53 plus a Cortex M4. So it is Pi-like in that sense. It's pretty powerful in that regard. It has the 40-pin GPIO Raspberry Pi-like expansion header. This is a drop-in sort of solution that you can use for anything where you may be doing something with a similar single board computer today. Now, the NVIDIA Jetson Nano is slightly different. NVIDIA, of course, is going to use their approach of doing inferencing, which is to use GPUs, or graphics processing units. So the NVIDIA Jetson Nano, and I love the fact that all of these, it's an EdgeML device if it has a giant heatsink on the top of it. And the heatsink wars have begun in earnest. The Nano heatsink is like this big. In the next 3 years, I think heatsinks are going to grow like Moore's Law, basically. I think that's where we're going. This is running 128 core Maxwell, so it can run 128 parallel GPU threads that run at 472 gigaflops, which is a whole lot of flops. It also has an ARM Cortex quad-core A57 in this case, lots of storage and some breakouts for actually integrating with your solutions as well. So there are other devices in this space, but these are just two of the more notable examples. And the point here is that we're moving beyond the power of trying just to rely on Raspberry Pi style single board computers, which are fine, and they're becoming more powerful, but actually building hardware that is purpose constructed for this ML inferencing type problem. This isn't something that you can solve with bigger CPUs. And because these are IoT class devices, you can add them easily into IoT style solutions, which I'll talk about in just a second. Now, I do have a Google Coral that's actually hooked up inside of this black box. People say that machine learning has a black box problem, so I went and actually built a black box to represent that problem. And so I have a Google Coral that's sitting inside of here. And for the first part of this demo, I will show you, and I'm going to assume that the demo crashed because this is prototyping hardware. So y'all forgive me for a second. I'm going to log back in and restart the demo. Detect server. There we go. Refresh, and my webcam here will come on. My webcam is streaming through the Google Coral, but if you look, and I will zoom in so that you can see it. We'll zoom out a little bit later. But you'll see this is actually the model. This is actually running a TensorFlow Lite model on the Google Coral device, and it's doing inferencing to create a bounding box around my face with about a 99% confidence. What's crazy about this is two things. One is that the inference time is about 7.6 milliseconds. To actually do a full bounding box around my face to actually get that data, and that's running at about 130 frames per second. So if you can see this, if you look at this in the computer vision space where you're actually in an industrial setting and you're monitoring packages as they're coming across a line, right? If you're monitoring an assembly line, to actually get sub 7 millisecond tracking without having to rely on cloud backhaul, without having to rely on a giant machine that's sitting on your factory floor is actually pretty impressive. And again, this is run locally on these devices. And now you can see why they need such giant heat sinks, because I mean, I heard it turn on the second that the fan on here, I heard it turn on like the second I refreshed my screen. So I'll show the rest of this demo in just a second, because I do want to go back and talk about where this leaves the Internet of Things. Because what I just showed, and you know, full disclosure, it's not obvious from my t-shirt. I work for a company that we don't make the Google Coral. We make microcontrollers. And so I'm interested in this space because I think edge computing and machine learning and inferencing on the edge is very relevant to the world of microcontrollers as well. And so I want to talk briefly as we end in the next 20 minutes or so about where this matters to the world of the IoT. First, I'm going to talk about the role that IoT devices play in collection and coordination with the edge, because that is still very, very important. And then second, I want to show how it's becoming increasingly possible, and this is cool, this will be my last demo, to actually do inferencing on microcontroller devices, like coin cell powered devices that can do this kind of inferencing as well. It'll blow your mind if it works. If it doesn't, you'll just have to take my word for it. And I'm going to say this again because I know I'm going to sound a little bit like a broken record. But again, machine learning data doesn't come from the cloud. It comes from the IoT, right? It comes from the world around us. And maybe I'm being a little bit permissive in my definition of the IoT, but the reason why I say this again here is because even with the rise of Edge ML, the IoT still plays a huge role in enabling these scenarios to work, right? Microcontrollers and their sensors are still the source of data that may be deferred to the edge for SBC or single board computers for inference, right? Even in this case, we are still collecting data that we're sending to the Coral that is actually doing work for us. But the other part that may be less obvious, but that is interesting here, is that IoT devices actually also can take action, right? So if you remember my industrial example from earlier, if we assume again that we have a single machine in our industrial set of washing machines that notices, our Edge SBC notice that there's a machine that's out of variance, what typically happens is that a lot of times is that the network will let a human know that the machine needs to be serviced. And this is useful, right? There's always a delay between a notification and when action actually happens, when a human being has to actually go and do something. But in these sorts of environments where edge inferencing is done, where inferencing is actually done inside of the IoT networks, you can actually have your IoT devices that take action as well, that they can actually put a device in standby mode or change its power state or change its operating state until it actually can be serviced. Again, the reason why predictive maintenance is this important concept in the world of IoT is because right now, maintenance work in the industrial world is a guessing game. Right? We service machines on a schedule because that schedule is built based on when we think the machine is probably going to break down if we don't get to it soon enough, right? If we have better insights around when machines are actually behaving and when they are misbehaving, we can predict, we can actually spot problems before they happen. We don't have to maintain machines on as much of that regular schedule, and we can actually save ourselves or make ourselves a lot of money on the other side. And there's also some emerging technologies in the IoT space that I think make this really interesting, right? I mean, my whole point in this part of the talk is to talk about the Internet of Things and machine learning through edge devices actually working together in concert to do interesting things. One of the ways that I think this is possible, and I encourage you all to take a look at moving forward, is IoT networks that aren't like our traditional IoT networks, but that are actually built more around mesh or peer-to-peer based IoT networking protocols. So let me explain what I mean by that. In traditional IoT installations, our architectures tended to be very hub and spoke, right? We would build solutions, whether they're Wi-Fi or cellular, where every node, and assume these little antenna things are nodes, every node on the IoT network has to connect to the central node, to the Wi-Fi router, or to the cellular access point. And if a node is too far away from that router, tough luck, it can't be part of the network. That's just the way that it goes. That's how these systems are designed. In addition, if a Wi-Fi device in this sort of a network, in this sort of an installation goes offline, then the network loses its IP address. Every device on the network loses its IP address and its ability to communicate with other devices on the network. So there's no concept of a local network in a traditional installation without the gateway, without the actual network device being online. So mesh networking, which I'll admit is not a new concept, but is maturing in many ways, is evolving to solve this problem because it operates on the principle that not every IoT device needs to actually be connected to the internet, right? And even those devices that are connected can be connected to one another so that devices can actually, through other peer devices, find a pathway to the internet, or that messages from the cloud can actually find a pathway back to those end node devices. This makes solutions more resilient, it makes them cheaper, and fundamentally more secure. And in this sort of a scenario, when a device goes offline or loses its connection, the network has an ability to auto-route, to actually intelligently heal itself and find a different pathway to the internet. Now, I mentioned that this has been around for a little while. So if you've seen some of this in the context of the smart home, you may have heard of Zigbee or Z-Wave. You may have heard of LoRaWAN in the context of larger area networks and the ability to connect low data rate networks at larger scales of miles or kilometers. And there's also Thread. Now, Thread is an interesting one because it was created by the Nest team at Google. So it's purpose-built for IoT class devices that run in low-power operating modes. This is interesting to many companies. Particle, the company I work for, is one of them, because it's a low-power mesh networking protocol. Every device in the network is IPv6 based. There's no single point of failure. It's tailored for these sorts of low-power devices, inexpensive radios that can actually do very interesting things. And so as you're looking into IoT devices out there, as you're investigating the space, keep an eye out for devices that actually do have mesh networking capabilities built in, whether you're using these in the short term or not. A few examples are devices from Particle, the Argon, the Boron, and the Xenon. All of these devices actually have mesh networking through thread built in. They all use the Nordic nRF5280 system on a chip, which is an amazing piece of silicon that actually has thread built in, as well as Bluetooth 5, and really a lot of space, a lot of storage. These are pretty powerful devices for running around 10 or 20 US dollars. But the whole idea is that these are devices that can, in the case of the first two, connect to the internet via Wi-Fi or cellular. And in the case of the third device, actually make up a network of end nodes that don't have to be connected to the internet, right? And a device without a Wi-Fi or a cellular radio is not only a cheaper device, but it's a more secure device because it cannot be accessed directly through its Wi-Fi or cellular radio. But the beauty of using a mesh networking solution in the context of machine learning is that edge devices, like I mentioned with the Google Coral and the Jetson Nano, are IoT friendly. These are devices that are meant to be broken out or added into other networks. They're designed to be added to existing IoT networks, and that's exactly what's possible in the case of the Google Coral board as well. And when you bring these devices into the network, having a mesh network means you're not bringing the Coral into the network, asking it to do inferencing, and asking it to be your domain controller, and asking it to be the thing that communicates with the cloud. You're just asking it to do inferencing, because the mesh network itself can actually handle brokering communications to the cloud, to the network. And that device that you've bought for inferencing can just be that. It doesn't have to be a Raspberry Pi plus some other things, and it ultimately will fail on you. So I want to look at a demo of this now. I actually showed off very briefly the Google Coral dev board through my last demo. And for this one, I would love it if I could have a volunteer. It'd be really cool if someone would volunteer to come up on stage and actually be a guinea pig for emotion detection in this demo. I will not keep the photo of you that this machine takes, I promise. Any volunteers? No one. Yeah, all right, come on up. Thank you. Yes, give him a round of applause for being willing to do this. All right. Let me make sure that I've got this set in capture mode. If you want to come over on this side. What's your name? Sony. Sony? Yeah. Very nice to meet you. I'm Brandon. You can come stand over here. Sony, all right. So let me... Glasses okay? Let's find out. I think glasses are okay. Let's find out. All right, so we've got the real-time inferencing actually happening. Sony, if you want to, what we're going to do when you're ready, think of an emotion: anger, contempt, disgust. You can base your emotion on what you think about this talk so far, so I'll know, get some real-time feedback if you want to do that. Okay. And then when you're ready, hit the green button to take a photo. Okay. Yeah, go for it. Oh no, did it crash on me like right at that second? Hold on, Sony. Hold on. Yes, it did. Y'all bear with me. It's not you, it's me. It's totally me.
Maybe it didn't like the glasses.
Maybe it didn't. You know what? It could have failed because of the glasses. I don't think so. It was fine. All right, let me rerun the serial monitor on here. Let me reset. I always have contingencies. A reset, refresh, pretend that last 2 minutes didn't even happen. Tony, okay. I'm getting the right thing. Okay, go ahead. Smile, whatever, hit the button. All right, so you'll see I'm getting a real-time update there, getting a change. We got 98% happiness and 3% neutral. I got a rounding problem, but that's all me. That's in the web UI. Are you 98% happy?
Yeah.
Is that correct? Okay. So if you like that, if you think that's right, hit the green button to say that it's correct. You're good to go. All right. So thank you very much, Tony. Appreciate it. Let's give him another round of applause. Thank you. So what's interesting about this, and I will admit this is a contrived demo, but the whole point is the buttons the lights, all of these things that are actually happening are not happening on the Google Coral. The only thing the Coral is doing is running the inferencing model. The process of starting detection, the process of responding to the result that comes in, sending commands to the network to light up the lights, and I hope you noticed that the lights changed as things happened during the demo. All of that is actually happening in the mesh network. This is all happening with the IoT devices, with the particle Argon that's got the Wi-Fi connection in the box, and it's actually serial connected to the Google Coral, and then these two Xenons that are connected to these NeoPixel strips, right? So it is an IoT solution where we're actually bringing edge inferencing in, but we're not deferring all of the processing to that device. And again, I will admit, it's contrived, but my whole point in sharing that is to sort of underscore the point that it's very easy to add these types of solutions into an existing network and do something interesting with them. But there's really more. There's more than just sort of saying, okay, we have these edge devices, now let's do some cool stuff with IoT solutions. There's actually two other things I want to talk about in the last few minutes that I have. One is that it's possible increasingly to actually do machine learning inferencing, not just on these $150 edge devices, but actually on microcontrollers. And the second, that there's some really interesting things happening with federated and distributed learning that will actually make it easier for us to break inferencing across barriers, across layers between microcontrollers and edge in the cloud as well. So first is TensorFlow Lite Micro. So TensorFlow is one of the most popular machine learning frameworks. It is curated very largely by a team at Google. TensorFlow Lite was created for running machine learning inferencing on mobile devices, but has increasingly been extended into microcontroller scenarios as well. There's an experimental branch of TensorFlow Lite called Micro, and there's been work done that actually can create models that can run directly via C++ code on newer ARM Cortex-M4 style devices. And at Google I/O, the Google team actually unveiled a board that they've been working on with SparkFun that runs TF Lite Micro and can be used for basic speech recognition. This is called the Apollo Dev Board, and it's $13, and it runs on a coin cell battery. Another example is from the MicroTensor team at ARM. And they created a similar TensorFlow-based library called MicroTensor. And they've actually released some demos that can run a CNN image recognition sample on ARM Cortex-M4 devices. So what's happening in this demo is they're actually using their fingers to draw a digit. And then based on a convolutional neural network built around the MNIST dataset, the Hello World of machine learning projects, it can actually take that from the device and show you the character on the screen. And you think, well, Brandon, that's great. My phone can do that. Yes, your $700 phone can do that. This is a $30 microcontroller. And that is really, really interesting that we can do this on very constrained devices. What's even cooler is that these two teams are actually merging their efforts, right? At Google I/O, the ARM and the Google teams announced that they would be actually merging around all their efforts around MicroTensor and TensorFlow Lite. So this will become a whole lot more interesting, and I definitely highly recommend checking those projects out. So for my last demo, I actually want to show this off because I have let me open up my, here we go. I have the Apollo, okay, I got my camera on. This is going to trip me up. Okay. I have an Apollo dev board here, and this is actually running a speech recognition model on it. You'll notice it does have a coin cell. It's not running on any other power. I don't have it secretly connected to anything. It's not secretly backhauling its data to the cloud and then piping in a response. This is the SparkFun Edge Apollo board, and what it's waiting for is for me to say the word yes. But I have to say it more than once. You'll see in just a second. What'll happen is I speak into it, is it's going to look for me to say that word, and then it'll light up the lights. These 4 LEDs are on sort of like a light bar, and I think it'll go from like blue to green. The more confident it is in the word that I said. It only recognizes one word, and that's yes, but come on. I mean, it's a $13 device. We can still be impressed with that. And I may have to say yes repeatedly in order for this to work. And if this works, I will have batted 1,000 on demos today. So there's a chance that it's not going to work at all. But we're going to try it anyway. So I'm going to get a little bit closer because you have to get close to it as well. And I'm going to say, and this is what I'm not going to ask for volunteer on because I don't want to make y'all shout what I'm about to shout into the device. Okay, here we go. Let me get in the right spot. Yes. 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 I see a little blue. Y'all see the blue? Yes. 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 There's green. Okay. See? All right. So I guess I actually had to really mean it before it would turn on. But again, this is really interesting. We're actually doing inferencing. There is a very, very tiny little model that is running on this $13 board that is then pulling my sound in from the microphone and then turning that into a set of ones and zeros that the model compares to and says, you have said the word yes, I'm going to turn my lights on a $13 device that really is not super powerful at all. This is state of the art, and so I will admit that there is a lot of work to be done here in order for us to get to a place where we can run these kinds of situations or these kinds of scenarios in production. But I think this is really interesting, and I think this is worth sharing because it shows that what's possible and where we're going to go in the next 3 to 5 years, where we can not just pull in $150 computers into our networks, but we can actually ask for these microcontrollers, for these sub $20 devices to take some of the load of doing machine learning inferencing for us. And so another area where this is kind of interesting, and I think some of these demos will enable, is allowing us to do things like federated learning to really maximize compute resources. Those of you that have been in this industry for a while remember that the whole reason that the whole cloud computing revolution kicked off is because companies like Amazon looked at their data center and they said, we're actually got a lot of idle time on our machines. Let's see if we can make some money off of that. Well, the same idle time problem that early cloud computing vendors had is an idle time problem that we have in IoT networks today, because most of these devices spend most of their time just sitting around doing nothing, sleeping, waiting for their next time to wake up to read from sensors and send data to backhaul data into the right place. And so wouldn't it be interesting if we could actually enable our models to be distributed so that they can actually be fit across environments? And this to me is really fascinating. I don't have anything tangible to share. I don't know of anybody that's actually actively doing this. This is all the realm of theory right now. But what many are talking about in this space is this idea that you could do early processing of a model, early calculations of inferencing on the devices when the sensor data is collected. And in the case, again, remember, a convolutional neural network is all about simplifying and grouping data so that features can emerge. So you get your early features from the microcontroller, you get middle features from your edge devices, and then perhaps even, and maybe even all the way to the end on the edge. And then if you need to, actually get your classification or your prediction to come out of the cloud device as well. And once you can do that, once you have devices that are capable of taking deconstructed models and deploying them in such a way, you can actually do some interesting things with over-the-air updates in models as well. And of course, as someone who works for Particle, this is one of the things that we love about our platform is the ability to do OTA firmware updates. So wouldn't it be cool if you could actually do over-the-air flashing of model updates as well, where you could actually do something very interesting, like taking a trained model, taking all of the data that comes in from the sensor network, updating and improving the model with real actual data as it comes in, taking the newly trained model and then deploying that directly into the edge or deploying that directly into the end devices. It's a pretty amazing idea, I think. So at the beginning of my talk today, I said that I wanted to convince you of 3 things. 1, that machine learning is really human teaching. 2nd is that training is meant for the cloud. And 3rd and finally, that the real work of ML is in the IoT. And I hope that I have done so and that you'll walk away with some excitement about what's possible. And so I want to leave you with really 3 calls to action. 1 is to explore machine learning inferencing with these single board computers. If you have the ability, a wherewithal to grab a Jetson Nano or a Google Coral board, Google has a USB stick version that'll plug into any Linux computer and it's cheaper, that does the same thing as well. Check out these devices. They're really fascinating. If you're doing any work in ML or any work in the IoT space, I think this is worth investigating. 2nd, is to look at mesh networking standards. Take a look at Bluetooth mesh. Take a look at Zigbee and Z-Wave and the work that's happening with OpenThread and the work that Particle is doing with mesh as well. And take a look at this for your IoT solutions if you're building them, because I think this is what's going to enable networks to be built that can handle this kind of ML inferencing in the future. And then finally, keep an eye on TensorFlow Lite and MicroTensor. I'm super fascinated by those projects. Again, I mentioned this Apollo dev board is $13. Support SparkFun, because maker businesses are like going out of business left and right. So grab one of these boards, please. It's actually really, really cool. And you can train it to recognize you saying no or another word if you want it to. That would be great. So that's all I got. Thank you all so much for coming today. I appreciate the time, and I'm happy to answer any questions afterwards up here.